Good. Yeah.
Do you want to start or want me to start?
That's right.
I'll start.
I think you start.
She'll come. All right, you guys. Thank you everybody for coming. Sorry again for the delay. Just had some technical issues with YouTube. Welcome to CSU Lunabotics CDR. A couple things on the agenda for today. Going to be going over what is Lunabotics. It's project management, systems engineering, mechanical engineering team, the electrical engineering team, software, computer engineering team, and then what we've done for outreach. And I'm going to let Trinity take it over for the what is Lunabotics and the project management. He already explained it. Just go over the Gantt chart.
Yeah, we already explained what Lunabotics was, so I don't think we really need to go over that again. So here's our Gantt chart. We've just been using it to keep on track. Unfortunately, we did fall a bit behind in the winter break because we originally planned to do our CDR a little bit before then, and then we had to keep pushing it back for technical reasons and people having like lots of exams and stuff. So that's why it got pushed back a little bit. We're still in the process of editing things. As you can see, we are mostly done with the design portion, and we are moving on to construction. Okay. So as a systems engineering competition, you are required to use a systems hierarchy. Basically what this is a chart that helps you visualize where your control gates are. Control gates are basically what you use to decide if you are ready to move on or not. So you start off with the SSR, which is basically just the conception of the Lunabotics competition project, what you are going to do, just the idea that you are going to compete. And then you move on to design and just thinking about design. That's where the PDR comes in. And right now we're at right before the building phase, which is the CDR.
Good morning. So now we'll go into the mechanical section. So chassis and tracks. If you saw our project last year, this is pretty similar with a few key changes. First of all, we have shortened the tracks by about 10 inches, and we have lightened the sprockets by removing much of the hub and surface material. And this year, instead of using a bucket wheel like we did last year, we're using basically a bulldozer. So tracks are reused. They're the same material, steel chain, 6061 aluminum grousers. Chassis constructed the same way as well, 2-inch aluminum tube stock, just welded together, simple, strong, effective. Idler arms, those are also reused, but instead of almost like a wheel, we're using sprockets as the rollers. That just means that we're putting tension on the chains instead of the pads this year, so we shouldn't have any bending like we did last year. And then one of the new parts that we're using are tran-torque bushings, which allow you to basically turn a nut and take the sprockets off very quickly instead of having to either weld or pin them onto the axles. And that just makes putting the tracks on and off much easier. For the excavation system, like I said, we're doing a bulldozer. That is also made out of aluminum. This is just aluminum stock that we are water jetting. It's about 1/8 to 1/16 thick, depending on which part you're looking at. That's bolted onto the carriage system of the linear actuator to allow it to move up and down. Linear actuator has basically roller bearings on this aluminum extrusion to keep it from turning side to side, since that is the lightest and most cost-effective solution that we have. It's fairly quick and it has very good positional accuracy, so software team has something good to work with. A mechanical bomb, here you have all the parts listed and color-coded as to what we have, what we need to buy, what we are reusing. That's pretty self-explanatory. Total cost up there, broken down between if we got everything donated and if we just had to buy everything.
All right, getting into the electrical side of things. I'm going to start off with our system layout. As far as the power side goes, software is going to handle the controls layout. You can see that we've got it separated into a 24 volt and a 5 volt system. Our 5 volt system is powered by a 15.2 volt LiPo battery. That's just because that's what gave us the runtime we needed. Couldn't find a 5 volt battery that had the amperage output that we needed for all the sensors and peripherals running. The motors are, we've got 4 traction motors, and each of those is going to have a power meter on it. That power meter is going to just give us another layer of robustness and measuring how much current we're drawing, being able to detect when we're hitting stall current, so we know that we don't want to keep running the motors in that direction. Let's say we're hitting a rock, boulder, crater, etc., that we can back up and not just burn out our motors mid-competition. There is a kill switch. You can see that up there. That's required by the competition to have. And then as far as on the 5-volt side, our two big things are the Raspberry Pi and the Wi-Fi router. There are other peripherals. There are cameras and a LiDAR, but those are going to be attached directly to the Raspberry Pi's terminals or USB ports. So they are not represented in here, but they are there. Here's our bill of materials. You can see that compared to mechanicals, ours costs a lot less. That is because mechanical covered the motors. Thank you, mechanical sub-team. We've got it separated into 24-volt, 5-volt systems, so you can get a good idea of what kind of parts we've got. You can see that the power sensor we're using here, I'm a big fan of those. Just, like I said, another layer of robustness, some more data acquisition. They can also be used to measure the 24-volt battery voltage as well as the LiPo battery voltage so that we can get some early indicators if they're starting to drain quicker than usual. All right, and then here's our bill of materials continued. This is just a lot of the miscellaneous pieces, parts, 12, 16 gauge wire, things we're going to need to run power to the motors. Connor's going to go over this, but the motors do take RS-485 communication protocol. So there is not a lot of fancy control work as far as like analog signals or anything that needs to go into it, which is really nice for the electrical side of things. You just hook up the signal wires and you should be okay. Here is a snapshot of our power budget. You can see here that where's our battery at? Maybe it didn't make it up there. Battery's good for, I think, 25 amp hours. Given we calculated that this would be a good battery based on the fact that our motors running at stall torque hit 8.33 amps each. Assuming that we were running our motors at stall torque for the entire half-hour run, we could still get about 45 minutes of runtime. So it's still over what we need. 25 amp hours doesn't sound like a lot, but it is more than enough for what we're using it for. Combined with the fact that we don't need any buck converters or anything to run the 5-volt system, you can see we've got operating voltage, no load, and stall current up there if you want any further details. If anybody has any questions, feel free to stop me. Yeah, what's up?
100 amps.
Where are you looking? That's assuming we're running everything at max current. So you can see how it's divided up between LiDAR. Here's our drive battery, Hall effect current sensor. So that's including everything here. Now
it's more like representative of like a burst current because it's not going to be running at that draw the whole time.
Jared, I think it's like somewhere in the 4 Newton meter range.
4 or 5 Newton meters.
Yeah.
The motors themselves, I think, only output like 2-point-something Newton meters, but then we have pretty beefy gearboxes on them that'll gear that down.
The motors are good up to 1500 RPM, which is way more than what we need. That's way too fast if we were going to direct drive it. So we can get a fair bit of torque out of it with the gear ratio that we've got. By the motors?
Yeah.
I think he said like 2.3 Newton meters each. We've got four motors.
And that's before you gear them down. So total, I think the total is upwards of 200 Newton meters of torque.
Yeah,
it's a lot. Gearboxes.
As far as housing goes, last year we had a 3D printed electronics housing box. We're going to try to stay away from that this year. It just turned into a big mess, trying to print it different pieces, parts, epoxy everything together. So given that we don't need any, the controllers for the motors are built into the motor itself. They're attached. So we don't need any extra hardware that needs to be enclosed. So we can just kind of keep the Raspberry Pis, any Picos, everything contained in a nice 16 by 11 inch project box. Those are readily available. Yeah, what's up?
Sorry.
We do. Was that in your slide, Jared? Or did you not end up putting it in there?
One?
Yeah, the one with the box in it.
That's the second slide, I think.
Second slide?
Yeah.
It's not up there.
No, total second slide. It's overall.
Second slide overall?
Yeah.
Okay.
Go back.
Yeah, there it is.
I see.
Yep, you can see it fits nice and neatly in there. We're still kind of worried about maybe getting to the latches themselves. We can always build some standoffs so that it goes above the top of the track and we don't have any clearance issues. Yeah, they have holes in the bottom. They just kind of have self-tapping screws. It's just going to be a matter of making some L brackets that bolt to the frame and then have holes that screw into the bottom of the box. Mhm. Right. I mean, as far as, safety wise, I would say our standard operating procedure is going to be making sure the robot is off before you go touching anything. You know, that's kind of a big safety concern. There's a lot of pinch points on this robot. It being a track driven robot, pinch points are a real concern. So that's, main rule, never work on the robot without the kill switch disengaged, engaged, however you want to describe it. There should be no power going to the motors whenever you're touching a robot. End of story. We're at 24 volts. That's just seemed what was realistic given what was on the market for 48 volt batteries and their price point, the amp hours we needed. Like we talked about, these maybe at 2.3 Newton meters. They're not as torquey as a 48 volt motor, but with the gearbox we've got, it should be more than enough. Mechanical did spend a lot of time sitting there looking through different motors, 48 volts, 24 volts, gearboxes, things like that, and a carefully thought out decision to make sure everything was going to play nicely and give us the amount of torque we needed. We do need a lot more torque than last year. That's why we did switch to 4 motors. It being a bulldozer design, we're not just carrying things, we are actively shoving it across the ground. A lot more friction, we do need a lot more torque. So that's kind of what drove that design choice. Yeah, so as far as dust mitigation, those project boxes do have gaskets around the sides. They are entirely sealed in that respect. As far as wires going in and out, I've been talking about this to anybody who had listened, but Molex just released a new MX150 connector. It is the pass-through connector you see over there. The old panel mount connectors they had were good if you had like sheet metal or real thin plastic, but those ones actually give you can kind of see in the back here a good bit of clearance to go into whatever type of material you might be using. So those have built-in rubber gaskets on them. You just bolt them to whatever surface they're mounting into, and you've got a pretty good seal. Molex connectors themselves do have built-in rubber gaskets in all the connectors. They also have plugs to fill in any gaps where you maybe don't have a wire or a terminal to keep things dust in this case, in more of a general sense, water, debris from getting in there. So big fan of Molex connectors. As far as high current applications, we are looking at Anderson connectors too. There are a fair bit of those lying around between different employers that people have. So probably not something we're going to have to buy, but they do make sealed Anderson connectors too that we're looking into for kind of those 8.33 amps per motor applications. But from what I understand, MX150s are good up to 20 amps themselves. So, and then I will hand it over to Connor. Does anybody have any questions? Okay.
Hi everybody, I'm Connor. I'm the software lead. So I'm going to briefly go over some of the computer subsystem and how we plan on controlling the robot. Spacebar?
Yeah.
All right, so quick hardware breakdown. This is the 5-volt system. So we have the Raspberry Pi as our main controller. And you'll see that a lot. It's used for both our autonomous and manual control system. Beyond that, using I2C, we're going to talk to a bunch of Pi Picos. Right now the plan is 1 per each side of the motors, being that both motors have to move together. I don't see a need to try to have 2 controllers. 1 should be fine. So setting up speed controls to Pi Picos. The Pi Picos can handle the RS-45, or also the motors are able to run on a simple PWM signal, depending on how much information we want to get back. That'll be a little bit of testing once we have the motors in front of us to see what the speeds and relative difficulty of all those are. Pi Pico also can control the linear actuator, similar style. Also, if we get to add any other sensors like power sensors, current sensors, stuff like that, we can also have those go to Pi Pico. I squared C being the simple bus to talk to all of them should make the wiring simple into the Pi, only using 2 pins. And nothing we're doing is really, really high speed, so we don't really have to worry about the baud rate there. So for manual control, a lot of this is specified by NASA already in the rulebook. So we have the pilot here, and we can go into a laptop. We'll probably use a simple Xbox controller that's just familiar to most of our members, and it's being used more and more now for controls. Ethernet cable goes into a NASA-provided switch. That is what will put the delays and will count up the amount of data usage. So the Wi-Fi rules are each way there's a 3-second delay that represents time taken to get to a transmitting station and sent to the moon. The moon is about 1.2 light seconds away from Earth on average. And then other transmission times, so they round it up to 3 seconds. It is a 6-second round-trip delay, which makes manual control very difficult. I've heard people complain about millisecond ping. This will be a 6-second ping. Anyway, so laptop goes into an Ethernet cable. We get to control what software goes through there. Go through the Ethernet cable on the other side to an access point. Traditionally, teams will use a router. We're hoping to use an access point, possibly even make our own with a Pi Pico. That will allow us to control what packets get sent. I did a project earlier this year where I was trying to minimize our data usage through this bus because, again, that is what gets our point deductions. And what I was finding is a router automatically sends out a lot of domain name server packets. Those are useless packets that are doing us nothing, that are going to cost us data. And so having more control will allow us to choose what packets get sent and even what protocols we're able to use. Patrick, go ahead.
Have you taken into consideration instability with control input when there's that 6-second delay when you input a control signal? If the robot goes one way and you realize that's wrong, it's going to take 6 seconds to correct that. And by the time that happens, it's going to be somewhere where it wasn't before. So how do you? Are you guys taking that into consideration with your control system?
Yeah, so I mean that's just a big push to work on autonomy. There's not really much you can do once you get to the point of having to use manual control. We can't reduce that delay. And so yeah, that definitely is a problem. We'll probably have to run the robot at slower speeds for manual control just so that we can maintain safety. But again, that's going to depend on what the regular rate of running for the robot is anyway. But yeah, no, that's just kind of one of the challenges of this competition is the fact that if you're trying to control it manually, you have to know that you're not going to see the results of your actions for 6 seconds, and that will slow you down significantly. I'm hoping to get a chance to get some practice in with that. I have a simulator that will simulate that 6-second delay and count the data usage. And so if we can have the robot running early, hopefully we can get some pilot practice beforehand, being that in most cases, teams will have to resort to manual control at some point over the course of the competition. Yeah, and then access point connects the Wi-Fi to the Raspberry Pi. It is a single point failure system in that if the Raspberry Pi for some reason goes down, we will not have a way to control the robot. We tried to get around that last year, but it added much more complexity than it was worth. The Pi has been reliable in our testing so far, and honestly, in most missions, if you lose the main controller, you're done anyway. So hopefully that doesn't happen. But any workarounds that we tried last year just added way too much complexity and got in the way. So brief little diagram on how our software breakdown works internally to the Pi. So we're going to get information out of cameras from April tags, and I have a slide in a minute explaining how all that works. We're going to use that to estimate our position, and that will go to state machine. LiDAR is what we're going to use for object detection. So it's a rotating LiDAR that we're going to put in the front of the robot. That will be able to hopefully detect both rocks in the way as well as craters. We are very confident that we can have it detect rocks. Craters are a little harder to detect, being that they're in the ground, but we have a possible solution involving angling the LiDAR, but we need to do more testing on that before we verify. Either way, if an object's detected, that will go into the same machine in the path planning so that we know to go around it. It is a deduction if we hit a rock or drive over a crater, as well as you can very easily get stuck. So we would like to avoid that at all costs. State machine is just basically we're going to tell the robot, okay, we are trying to go to here. So it's the basic idea of the run is going to be you start off, you figure out your orientation because that's randomized, and then you want to get to the excavation area, so path plan there, and then go from the excavation area to the build area and back and forth. Being that we do not have to dump this year because we are a bulldozer design, that simplifies that. It is simply just a track back and forth to the excavation area, back to the build area, which will save us a little bit in that process. But that's pretty much what that part of the program will do. Path planning is going to be very simple, probably something based off of the graph theory. Not really a big importance right now, being that we need to work on the peripherals, but yeah, it's kind of plan there. And then they'll just go to the motor controllers, and that's just setting specific speeds to specific motor controllers, so we know how to move. Any questions on that? Ready? Yeah, so a little breakdown of our localization, so you can get a better image of that. So this is the arena. This is specifically the one for NASA, the NASA Kennedy Space Center. The one at UCF is slightly different, but the same basic idea. So we start in the starting area. We start a random orientation. We are allowed to reorient ourselves within that box, but that takes time. But we probably will try to do that. Our plan right now is to put these things called April tags onto the corners of the arena so that we have an idea of where we're at. So April tags are these QR code looking things. They're used commonly by First Robotics, which is a high school robotic competition around here. Hannah will talk about that a little bit in a minute. But there are already known programs that are able to find those images inside like a camera view, and from it get a distance to and an angle of where you are relative to the tag. So if we put tags at each of these corners and label them in the software, then as long as we can see one of the corners, which you will be able to, their only obstruction here is this column, but even if this is blocking most of it, there's still always going to be a corner you can find. You are able to get your position relative to those tags, and we will know the initial position and orientation of those tags as we are allowed to place them. So in the competition, they have a set of mounting positions. They're a PVC pipe with a hole drilled in them that we can place any beacons on. And so, yeah, so we will know their initial position and their starting angle, and that will let us figure out where we are inside the arena. For inside the arena, we know the dimensions and we can program that into the robot. We will not know where the obstacles are. That is where the LiDAR comes in. So that's why we can't start with the starting path, but we already do know where the goal is and where our starting position is relative to each other. And so those can also be hard coded in. Any questions on that?
Like the error when we know like the accuracy is
Yeah, I definitely would love to be able to try to use multiple of them. That involves mounting more cameras. It shouldn't be a big issue. My concern right now is the RAM usage. We can talk about using a second Pi just for that if that's the case. But yeah, no, I agree there's issues with that. I've been told also, or from what I've seen, it's a lot easier the bigger you make the tags. Being that we can set the tag size, we can do that to help ourselves out. That'll make them easier to detect and hopefully reduce the error. Any other questions on that? Anyway, with that, I will give it over to Hannah about outreach.
Hello, everyone. Good afternoon. So as Gunnar said, I'm Hannah. I'm the head of outreach with with Lunabotics. Sorry. Over the course since last May of 2024 to January 2025, we were able to complete over 300 hours of community service and outreach. That includes a NASA Career Day at Lorraine JVS, AWT Robotics, which Adam will talk about in a second, STEM tutoring, and First Robotics at schools of Garrett Morgan High School, MC Squared STEM High School, and Magnificat High School, as well as various events and competitions, mostly through First Robotics again, with Curiosity Open, Corey, and both the Buckeye and Miami Valley Regional. You want to talk about it?
Yeah. So I'm helping out with AWT Robotics at Riverside High School in Painesville, Ohio. And a little bit different than First Robotics. It's a BattleBot design competition, so it's more about the design and manufacturing principles that go into creating and fabricating a robot from scratch that can withstand some brunt. So on the right side, you can see that we have sort of a hexagonal shaped robot this year. But there's a lot. Sometimes, sorry.
What does AWT stand for?
It is. I actually don't remember. It's some. I'll get back to you. I don't remember. But it's a foundation that is based in Painesville, Ohio, and they do like stuff in the northeastern United States area. They have a regional competition every year, and I think 50 high schools participate, and there's brackets. They do a 2-day competition, and then the winners from those go to a regional competition that happens for, I think it's just the general northeast United States area. And yeah, so this year we're actually working on a robot where we have to focus on software. It's a multi-brain robot, so it has 2 motors, but it spins radially, and it has to control its movements linearly while it's spinning at 10 RPM, for example. So, or not 10 RPM, 10 rotations per second, which is a lot of RPM. So that is something we're doing for outreach.
And then to counter Adam's BattleBot design, First Robotics is more about cooperation between teams and getting a task done through their design and systems of their robots. So moving on, from the beginning of February 2025 to the present, we've completed over 100 hours of community service at, again, the Garrett Morgan School of Engineering, MC Squared High School here on campus and down at the Science Center, as well as Magnificat High School. We are welcoming everyone every Saturday to go down to the Great Lakes Science Center and help to volunteer. The Science Center has 5 to 6 amazing teams right now that are doing amazing things. And that QR code right there is a invitation to sign up for the Buckeye Regional. That's going to be right here in the Wolstein Center, April 3rd through the 5th. And again, the various upcoming events is that Buckeye Regional, April 2nd, which is the setup day. The actual competition does start on the 3rd through the 5th. We're also having the IEEE STEM Day at Progressive Field on May 14th, which the training is May 4th. Yeah. So anyone interested in that, please let me know now. What? March 4th. March 4th. Sorry, March 4th. All right. Any questions on outreach? Yes. That is your Riverside High School.
Riverside High School in Painesville. We just finished our design phase, so we've started manufacturing. Competitions in April or mid-April, so we're just starting building them.
You guys are going to be competing at Lorraine County.
It's at Lakeland Community College.
Lorraine County Community College, right?
Lakeland.
Lakeland.
It switches though, so sometimes the event is hosted at Lakeland, sometimes it's at a nearby facility called Freedon, so it'll depend, but it's generally in the Lake County area.
Gotcha. Thank you.
Mm-hmm.
All right. I believe that brings us to the end of the presentation. I'm going to have all the officers come out. And then, is there any questions?
For mechanical design, what, I'm sure there's what qualifications do you have for product design? Because it's too much time for this rocket. Support up with the light rating of the design.
Yeah, so the light weighting minimizes basically the thinness of the material with the circles, and I ran those through FEA just to make sure that they would hold, and they hold.
Now, is that FEA done on how dense was that mesh, and was it done with only one spoke, or was that what applied to all?
I applied it to all of them, and the mesh was pretty dense, I want to say.
When doing FEA, it's best to apply the village one and then divide by the amount of torque and then divide the torque by the number of sprockets, because then it's I'm sorry, splits, because then it's applying the load per tube, not the entire load all at once.
I also did the shear calculations for the minimum cross section on the spokes by hand as well, just to double check it.
Yeah. All right. Then, for the axles, are those also going to pull up?
Yeah, the axles are like half-inch steel axles, I want to say, and they'll hold.
What's the margin you put on this calculation?
I think it's 1.5. Yeah.
I'm just curious, what systems or mechanisms do we have in place for the linear actuator to make sure it doesn't get gummed up?
So it's not shown in the model here, but once we're actually done building, we're gonna put basically a rubber grommet over it, or a shield, a dust shield, basically that moves with the carriage,
Oh, okay.
so that it keeps dust out.
There's something missing from the presentation in general. Is there any systems engineering slides?
There was one at the start, I believe. There was a system hierarchy slide.
Okay. Yeah, we got that.
Did you have any others?
Is there anything that like addresses requirements documents? Test plans.
There is not in this one.
Points of verification should be in the.
So we have a timeline for our test plans and verification. Did you guys go over any of that in any previous design reviews as far as?
We
Not
wouldn't
like
write
specific test parameters. No.
Okay. So
That's happened. Yeah, I guess like if I was gonna talk about like I'd address
you have any?
same thing with that. I'm having trouble understanding. And you have this sort of address, but I don't know, the integration between
Can you be a little more specific? Maybe I can.
there, it doesn't seem like the mating. How are the parts?
Mechanically?
Yeah.
Well, so mechanical's got all of the at least big electrical components modeled, your motors, and then they've got the gearboxes. They've got where they're going to fit in the robot. As far as the motors go, I could have sworn I had a picture of it. Maybe I substituted it for those symbols.
Yeah, the motors make sense. I'm talking about the electrical boxes, the various components.
Yeah, so as far as the power sensors can really be located anywhere on the power supply wires to the motors themselves. Really what they are is it's just a splice in and then out. They're good up to, I believe, like maybe 25 amps. So they can handle a fair bit of current. I could probably pull that up if you'd like me to, as far as the data sheet, but they're very small. I had a picture of it, but I think I omitted it once Connor said he was going to do the systems diagram for controls. But that being said, all of the electrical components themselves are very small and can fit in that box if need be. Everything that's not the motors, that is.
I guess you are correct in saying that we don't have like a mount for the LiDAR cameras yet. That would be the thing we're missing.
There's a lot of mechanical structure that seems to me is like a CDR level. Yeah, I think in the next weeks here, addressing all your interfaces and how those electrical components are going to get mounted onto this chassis. You may have more detail in the model than
That being said, too, we did finish cutting and milling everything on the mechanical end. It just needs put together. And then once that's all welded and assembled, we can really get a better idea of how everything, like you can look at it in a 3D model, but a lot of the fine tuning of where the camera and the LiDAR are going to be placed is going to have to be done with testing, right? Like what works and what doesn't. So that's probably why it's not in there now. I can't speak explicitly for why.
We know it'll be between the brackets that mount the box and the linear actuator, so it'll just be, yeah, like Kevin said,
Yeah.
a matter of testing.
Okay, so yeah, I mean, if it's not in the model itself, I just have some, I guess.
We have a parametric or a group of parametric mounts for different sensors that once we actually do the testing, we can figure out which parameters work best, 3D print them, and then put them on the robot in like a day.
Okay, yeah, that makes sense. Yeah, I guess just like address some assembly documents that you can hand out things to other mentors,
Mhm.
or is there other members to build, and they've got something to look back on.
Okay.
The robot's supposed to be put together.
I think what Chris is saying very politely is you guys don't have a schematic. You guys don't have any examples of code, testing, anything. I mean, those things do exist. A lot of it was just kind of simplified for this. As far as code, I know.
I've heard like a lot of plans and like.
We're moving away from Roth and developing a custom framework because we don't think we have enough independent systems that.
Yeah, no shit, and you're gonna run it all from the top.
Mhm.
You're gonna run the AI framework or localization framework and a motor control framework.
Mhm.
And from which Pi? Like it says Raspberry Pi, but it didn't say whether it was a Pi 5 or
We have 5s.
5. Okay, so that gives me a little more faith. But I mean, guys, this is your CDR. Like I'm seeing a lot of stuff here that I would expect to see during like a systems design.
That's a fair assessment.
So, when's your guys' competition?
May 10th.
Makes sense.
May 10th. That's what, 2 months from now? 3 months? You guys think you're ready?
All right, now, no.
We are still ahead of schedule compared to last year,
That is not a great metric. Okay.
which isn't a
I
great
was gonna
metric,
say,
but
because like if we're talking about last year, it's kind of like, dude, making a ROS framework. I mean, Connor, you know this. You studied this for like, it's not something that you just do in 3 months, unless you guys want to put a lot of all-nighters into it. And you guys still have midterms, you still have finals and homework. I mean, so I mean, and welding. Are you guys, but are you guys have planned for welding the aluminum together?
yeah, we have a member that can weld aluminum, and so we'll weld the frame and all the aluminum parts with that member.
Yeah, and the project management side. I mean,
We have been using decision making. Should have. That's something
Yeah,
that
I
also
would
had trouble with the system. I guess originally there was a different systems engineer. So that.
Yeah, it's I get it. You just didn't address it. But yeah, I guess at this point, with just the I don't know, it would be like getting what these guys are out. I would suggest like a Delta's CDR before you guys get to the actual competition.
The other thing I would like to say.
When you get like a little closer, maybe a month from now, just review. Is that I think there was a lot of like just I don't know confusion when it came to the competition So just so that all your members have a, clear direction before you get into the sprint at the end of the year.
You guys have been super professional. Like, I'm really impressed with how you guys spoke and how you guys have presented this. But, I mean, AWT, me and you were actually in AWT. And you remember, like, if we, like, in a real high stakes environment, you're talking like thousands of dollars. Like, if you don't have shit ready, it costs money. So just remember that going forward into your guys' careers, that if you're going to get to the point where you're at a critical design phase, you gotta have value that you present. Like, I'm talking schematics, code, simulations, testing, prototyping. I mean, am I wrong here?
You're not wrong. There's who does testing designs, schematics, show some sort of proof of something built already.
Yeah. So
Even if it's just a prototype.
on top of those are all very very valid criticisms, and I appreciate you bringing that up. So again, it's not new, and we definitely should have prepared a little bit for it, a little more. But SGA, that's very much like a scapegoat. But
Yeah, and I'm not trying to say this to be a dick to you guys. Like, I care about you guys.
no, I appreciate
you
it.
guys to go into your careers after this. Like, Mr. Nachman would not have, like, he would lay it down to us hard, not because he didn't like us or whatever, but he wanted us to succeed. So I'm going to pass it on. I want you all to succeed. I want you guys to do well for this competition. Make sure you guys have your stuff ready, or else it's going to bite you in the ass and you're going to be stuck with what happened last year.
Agreed.
Think of where you're standing right now. If you can address your top level requirements, your mission success criteria, and flow those down into your like system design requirements, you essentially should say I think you've addressed everything to adequately say that you've completed the PDR, which is good. Because even just getting through that as a team is not a easy feat. I think if you mop up some of these areas, you'll be able to get everything that needs to have your CDR done and ready to confidently build this thing and go win the competition.
Like, you guys are a good team. Like, even from last year, like, a lot of teams struggled with a lot of stuff, and you guys still managed to come out on top compared to a lot of teams. But there's room for improvement. Just remember that going forward.
One thing I would like to say too, that I've been waiting to kind of sneak in here. The electrical sub team being kind of in a limbo, waiting for motors to come in and waiting for different things to get assembled. We have started putting together a test bed. It's actually sitting in the office right now. Probably should have brought it with me, but it is a platform that's going to allow us to test a lot of softwares, locomotion, localization, things of that nature. Something that I think we really definitely improved on last year. Again, still a lot of areas we still need to improve in, but I thought it would be worth it to point that out. I meant to bring it up earlier, and I did not. So
That's okay.
Yeah,
That's
that's-
good to hear.
That is good to hear. And that's the testing approach and prototype. That's what you would put in those like project management.
okay.
So that's good. That's one of the criteria.
Okay.
So, well, I did think the presentation skills of this presentation.
Yeah, I agree.
Everyone
You
did
guys
a
all
great
did.
job with that. I wouldn't say, like, I'm looking at the front of this sheet. I don't think other than the technical and the exit criteria, you know, anything that was presented. Impressed with that.
Yeah, you all spoke very clearly and concisely. I mean, honestly, it was pretty industry level. You guys did well.
Another thing I'd like to bring up when you mentioned the mechanical schematics, those exist, but since there's so many parts in the robot, I didn't feel like including some and then not others in the CDR would be best use of time.
Would you say that it would be valuable to bring in at least some for future presentations?
Yeah, show us and we can see it. There's,
If you're gonna talk about simulation, any simulation at any level will have proof that to show that it was done. Because if you say you did it, you have proof that you did it as well.
Gotcha. Thank you.
For any simulation, mechanical, electrical, so just have proof that you did it. Don't just say you did it because, well, I take your guys' word for it. If you were, if you're designing this as like an actual product, and you say you did something, you have to have proof that you did it.
What I would recommend is the way you do this in industry and whatnot is you end up having like a PDR package, a CDR. So you want to put all those schematics that you do have, test plans that your systems engineering, if your project management has developed all those requirements, you want to put that all together in a package that you can send out to your review board before they even get to the review itself. If your review board is doing their due diligence, they should look at that.
Like just some sort of briefing, I guess.
Okay.
All right.
It doesn't really have to be organized. The only thing you have to do is essentially make a single document and the Excel sheet that says, here's the document, like if there's a document number, what it actually is.
Okay.
The fact that we can get this level of nitty gritty on what you guys are missing is just a major improvement from last year to begin with, though, because you guys are getting to the point to actually refine your project development cycle.
Maybe once we have it more in a precise area, we'll create another slideshow or something and share it with some of you guys.
I think the last thing I just want to say, especially as you guys go forward into your careers and competition, the biggest thing I've learned just being in the industry for like the past 7 months, which is but the biggest thing I've learned is that if you're going to present a case, having data goes a very long way. Having data, having stuff to back up what you're talking about, you know, it brings value when you can show, hey, this is what we've done, and can show the numbers in a way that makes sense to people who may not know what's going on. You know what I mean?
Mhm.
So, great presentation. Great job speaking. You all did well. Don't do too many all-nighters. Don't skip on your finals or anything. Nice to each other.
On the technical side, can you guys go back to kind of the software electrical integration? 'Cause I think it's there. I think it was just
This one specifically, or is there another one you're looking
yeah,
for?
is this the only like
Yeah, this is like the low voltage system. The
Yeah.
5 volts.
I mean, there's a little bit on the manual side, but the manual side is off the robot. This is the that's kind of the off the robot hardware. But that's pretty much defined by NASA.
Yeah.
We don't really, we get to change pilot to laptop, and then they don't tell you what protocol you have to use on that Ethernet cable, but it's an Ethernet cable, so it has to work on an Ethernet cable.
Yeah, I'm not really worried about this part.
Yeah. So if you go back to, so basic idea is to do a web from a single controller to a bunch of microcontrollers to handle the smaller tasks.
Do you have an electrical diagram for this?
Not a nice one made on the computer. That's something where I'll take the blame for that. I definitely should have put a little bit more time into making these diagrams, but
I think if you throw a schematic together, getting a physical schematic.
mhm. Okay.
It's also just, it'll make it a lot.
Okay.
I know you guys, you're not giving any custom search for it,
Not this year. No.
Very
but you can
minimal.
still make a system.
One
schematic.
one thing we have looked at that I would appreciate some input on is potential noise still between the 5 volt and the 24 volt system. Now we are using brushless DC motors this year as opposed to stepper motors.
Oh, are
and
you not using separate?
we are using a separate battery for the logic. However, they do still need to be grounded together for the RS-45 signals to communicate or propagate reliably.
Not if you isolate.
Not if you isolate them. How would you say? Because
Well, is your motor driver taped?
no, it does not. That's one kind of downgrade we had from last year. That was all opto isolated. It had all that stuff built in, and this one does not. So something that we're looking into is either making our own boards for opto isolation or looking into different methods of just ground isolation between the two systems. So if anybody has any recommendations for
We might
Well,
actually be able to ground at the microcontrollers, isolate the microcontrollers, because I squared C is differential.
okay.
And so you might have to ground the microcontroller to the motor it's working on, but then it's only that PWM or
We
RS-435.
talked about this before, where the microcontroller might be floating at one voltage, the other one might be floating at like 13,000 volts of static electricity, and it's not good. We'll talk about it later. Sorry, what was that?
Yeah, so if you single point ground, uh, I think if you single point ground, you're gonna have some noise, but what you really need to avoid is having any crowd in the system. So you're tying these to chassis, or
As far as the motors are, yeah, we were looking into tying maybe just running a conductor outside of the box, tying that to chassis too, as long as they're all on the same ground.
yeah, I mean the most important thing is addressing the return path. So if you look at where the signal is flowing to PWM those motors, make sure that you've got a signal line and a return line twisted pair together. You need to shield and keep that area short. And then yeah, try to just keep probably the single point ground near the motor is the best way to do that. But yeah, if you end up having multiple ties to your chassis or multiple ties to the plane, you're gonna end up with ground.
Okay.
You can also break that. Part of the reason why you use isolation, optical isolation, you're breaking the loop.
Right.
That's all that really does. It's the whole point of that is to break the ground supply loop.
Okay. Thank you.
Yeah.
Any other questions, comments, concerns? Don't be shy. Yeah.
So, quick question. Are we going to have any redundancies in handling the robot? That's why I'm just confused by how we're going to make.
Oh, like if you're like fixing something in the robot?
Yeah.
Yes. So we have to put a kill switch on there anyway, and that cuts off power to the 24-volt system. It does keep the 5-volt system running, but I don't really see the 5-volt system as being any bit of a safety concern.
We also are going to have LED indicators on it this year, so you'll be able to see if there's power going to the main drivetrain.
Well, all of your batteries are safety concerns. Are they lipos?
The 15.2.
Lithium iron phosphate.
5,
Right.
is the
Even the
5-volt
15 volt one? I thought it was a
Sure.
lipo.
Any lipo.
The smaller one is a lipo.
The smaller one is a LiPo, yeah.
Yeah.
So, I mean, if you're worried about pinch points, these kill switches, those are like industry standard. They're used in industrial settings. They're extremely safe. As far as shorting the battery, that is definitely a safety concern. And that's mostly done. So, it's going to be in the plastic box whenever you're handling it, right? And a lot of that too is good connector design and harness management, where you can intentionally design it to make it hard to short, right? So the connectors are only going to be able to go in one way. They're recessed connectors, so you can't like set it on something and have it short out. The only other thing would be like getting it pinched on something, and if you're following the rule of working on it while the kill switch is on, it shouldn't get pinched. Another thing to implement is just periodic checks over all your cables, right? Look for call them preventative maintenance checks and services. Go over, make sure there's nothing that's broken. Look over your insulators, making sure there's no cuts, no gashes, things of that nature. So,
Are you buying some snakes?
or just I was going to take it from work, to be completely honest. There's like tons of it, but yeah.
No. You are not exceeding 30.
Not off
That's
the
like
top.
the minimum amount that you need to consider a shock.
Well, not a shock, but the danger level voltage where you can really get yourself in trouble. I would recommend.
Noted. Any other questions? Comments, concerns? Akshat, you've been kind of quiet.
Feel free to touch
Feel free to what?
Feel free to touch the 24
I put my hands on 56 volts.
Not that bad.
All right. Well, if that wraps up everybody's questions, I will let everybody come get some food. Just after all those compliments on how professional we are, we had to throw this in at the end.
Had to sneak a little personality in.
Just be lucky there were no fire suppression systems or hydrogen generators in this presentation.
We had a whole fuel cell slide ready.
Yeah. There's pizza, there's cookies, there's drinks. Again, there's a lot left. I don't want to eat all of it. I'm sure some of these people would like to eat all of it, but take more, seriously. Plates, napkins. Again, thank you everybody for coming. And that concludes our CDR. Can I stop streaming?
No questions from online, right?
Are there any comments in the video?
I don't think we've seen it.